All right, yes, so all right, so welcome everybody to this edition of the coaching seminar. Today we are happy to have Chitrarekha Sahu from Mohali, and she will speak about iterated and generalized iterated integrals. Please.
Thank you for the kind introduction. And I also thank all the organizers for arranging coaching seminar and for inviting me. And I will talk on a joint work with Sais and my supervisor Srinivasan. So let's start the talk. So the plan of this talk is like we will go in three parts. So in three sections. So in the first section, we define generalized iterated integrals and characterized Picard-Ratio ring if the Galois group is unipotent algebraic group. Like characterize the elements of the Picard-Ratio ring, and as an application of these results, we see application to generalization of Liouville's theorem for elementary and integrable elements. And then we see elementary relations between generalized iterated integrals. So before that, let's set up some notations. So we will denote F to be a differential field of characteristic 0, and where derivation will be denoted by this prime. And CF denote the field of constants of F, which we will assume to be algebraically closed. And F partial, this ring is the ring of differential operators over F. So let's recall this definition of Picard-Ratio ring. Differential ring T is called a Picard-Ratio ring of for an operator L of order n if T is a simple differential ring and it is generated by the full set of solutions and inverse of the Wronskian and all their derivatives. And field of fractions of a Picard-Ratio ring is called a Picard-Ratio extension for an operator. So we assume that the field of constants of F is algebraically closed. That is needed to ensure that the Picard-Ratio extension exists for a given operator.
So now what does it mean, a simple differential ring?
So there is no non-zero, there is no non-trivial differential ideal of T.
Okay, thank you.
Yeah. So if E is a Picard-Ratio extension of F, then we denote G over F, which is a set of all automorphism of E, which commute with the derivation, and this is called a differential Galois group of E over F. So this is a simple example where if we take F to be Cx and derivation is d by dx, then the Picard-Ratio ring, Picard-Ratio extension for this operator is the field generated by a logarithm of x minus c. And this case, Galois group is additive algebraic group. So as we know from the Colchin's result that the structure of Picard-Ratio extension, if the Galois group is unipotent algebraic group, and that is if he is a Picard-Ratio extension of F, and the Galois group is isomorphic to product of n copies of additive groups, if and only if it is generated by integrals of F, and it is unipotent algebraic group if and only if it is generated by elements T1 up to Tn, where each Ti prime is in the field generated by T1 up to Ti minus 1. Colchin gave structure for a Picard-Ratio extension. If Galois group is unipotent, we will give a characterization of elements of the Picard-Ratio ring if the Galois group is unipotent algebraic group. Like in this section, we will first characterize elements of the Picard-Ratio ring if the Galois group is unipotent, and then we will provide a new factorization which is different from the factorization given by Colchin for solvable groups. And so the new factorization is for Galois if the Galois group is unipotent, and if a Galois group is unipotent Galois group is given, unipotent algebraic group is given, then we will also give an algorithm to how to construct L with this new factorization, such that the differential Galois group for L is the given U. So let's see this notation first. So if F is a tuple, then we define this operator which we denote by LF is a operator or which is product of FIs and partials, is a linear differential operator of order n. Then Roque and Singer, they define that an element eta is said to be iterated integral of F if there is an n such that nth derivative of eta is in the base field F. Now we will generalize this definition to definition and give that we will say that an element eta is said to be generalized iterated integral of F if there is a positive integer n and a tuple F such that LF of eta equal to 0. In particular, if we take this in this second definition, if we take F3 up to Fn to be 1, then eta will be a iterated integral of F. And from the work of Roque and Singer for iterated integrals, we started this work for generalized iterated integrals. So let's see this example where this if f is cx with a derivation d by dx, then this die logarithm which we denote by L2 of x is a generalized iterated integral, and LF of L2 of x is 0 for f given by this 1x minus 1x. Roque and Singer, they already proved that if f has an element x such that x prime is 1, and if eta is a iterated integral of f, then the differential field generated by eta is a Picard-Bessel extension of f such that the Galois group is unipotent, and the Galois group is unipotent. We can also say that in this case E is generated as a differential field over f by an iterated integral of f if and only if is a Picard-Bessel extension of f and the Galois group is commutative unipotent algebraic group. And from these results, we can generalize these results to the case of to the case for unipotent algebraic group, and we can prove we can say this if E is a Picard-Bessel extension of f, then these following statements are equivalent. The first one is there is an f such that E is Picard-Bessel extension of f for an operator LF of this form, and if and only if the differential Galois group is unipotent, and if and only if the element of the Picard-Bessel ring is the set of all generalized iterated integral in E of f. So this third characterizes the element of the Picard-Bessel ring if the Galois group is unipotent. Then so the proof for this theorem first implies 2 and 3 implies 1 are simple. So we'll give the outline of the proof for 2 implies 3. So we assume that the differential Galois group G over F is unipotent. Then we know that the Picard-Bessel ring is given by is the ring generated by some element eta 1 up to eta n, where each eta I prime belongs to the ring generated by eta 1 up to eta I minus 1. And we prove this by using induction on n and degree of polynomials. So for that, we assume that every polynomial in eta I of degree less than n is a generalized iterated integral of f. And then we take a polynomial p of degree L in eta I. Then we like by assumption is AL, the coefficient AL is a generalized iterated integral. So there exists some G such that LG of AL equal to 0. Now if we apply LG to P, then this will be of degree less than L in eta I. And so that by assumption LG of P is also a generalized iterated integral of f, and that will imply P is also a generalized iterated integral. And so this proves that all the elements of T are generalized iterated integral of f. And now if an element is a generalized iterated integral, then it is a solution of some differential equation over f. So it is in T. So this proves that so T is the set of all generalized iterated integrals in E of f. So this proves this 2 implies 3. And so Colchin, he proved that if an operator, monic operator of order n is given, then L can be factored as a linear factor over algebraic extension of F if and only if the connected component of the differential Galois group L is solvable linear algebraic group. So in particular, if the Galois group is unipotent, then these AIs are actually logarithmic derivatives of elements of F. So, and from our results, we can also conclude this proposition that if a monic operator of order n is given and is the Picard-based extension of this operator, then the differential Galois group is unipotent if and only if there is a tuple F such that tuple F and an element, non-zero element Fn plus 1 such that L can be factored as LF and Fn plus 1, and that is product of this partials and FIs. And in fact, if we know the operator, the factorization of the operator, then we can find a basis of the solutions of L, and those solutions can be explicitly written in the terms of integrals and using FIs. And we can do converse also, that if we know basis of solutions of L such that with respect to this basis, the Galois group has representation in the inside UNC, the set of all upper triangular unipotent matrices, then we can find the factorization. So if you know the solution, then you can also find the factorization in that case. And this can be used to find the algorithm that if you know the solutions, then we will find the factorization. So we'll see that later. This example where if f is cx and derivation is d by dx, then for this given f, the c basis of the solutions of LF that can be explicitly written in terms of this f is given by 1, 1 minus x, x and x. And this V4 is the trilog, where this V4 is the trilogarithm, and the Galois group in this case is a non-commutative proper subgroup of U4C. Now, if like a Kovacic proved for the unipotent case that if a unipotent algebraic group is given and a base field which is Cx is given, the base field is Cx, then we can find an operator so that the Galois group for that is given unipotent algebraic group. So we provide an algorithm to find f so that if the ideal of defining ideal of U is given, then we can provide an algorithm to find the operator LF so that its Galois group is the given unipotent algebraic group. And using Grosvenor basis technique, we can also find f if the basis elements of the Lie algebra U is known. So let's see the outline of the algorithm. So this few steps is the technique used by Kovacic. So it is the same. And if we have a unipotent algebraic group U inside UNC, that is upper triangular unipotent matrices, set of all upper triangular unipotent matrices. So if I is given, then we find a basis of the Lie algebra of U. Let's say it's x1, x2, xl, xm, such that this set d pi of x1 up to d pi of xl is form basis of the Lie algebra of U modulo commutator subgroup of U. Then we take some elements AIs which are C-linearly independent modulo this set. Then for this matrix differential equation, y prime equal to AUY, where AU is given by summation of AIXI. For this, the Galois group is a unipotent algebraic group. So this is the same technique which Kovacic used, and proved that for this y prime equal to AUY, the Galois group is U. Now, if we take R to be this ring generated by Zij, where the derivation is given by Z prime equal to AUZ, then by using Torsor theorem, T is R modulo the ideal I extension is the Picard ratio ring for the differential equation y prime equal to AUY. So this capital Z modulo I extension is the fundamental matrix for the differential equation y prime equal to AU1. So we have a matrix differential equation and the solution. Now using cyclic vector theorem, we calculate a B such that this AC defined by this is a companion matrix. And then the next step is we will find a B naught such that the one entry of B naught BZ is 1, and so that the A naught this matrix A naught is again a companion matrix. So here I'm not writing what is explicitly B naught, but in the paper we have written that what is B naught. That can be written explicitly. And then we take the first row of this first row entries of this matrix B naught BZ, which we denote by yi. And if you go modulo yi modulo I extension, then these are the solution of the scalar differential equation. Scalar differential equation which can be obtained from the matrix differential equation y prime equal to a naught y. A naught is companion matrix. So from that proposition, we know that if we know the solutions yi modulo I extension, then from that we can also find fi's, and those can be given by those can be found by taking gi modulo I extension. So, and from that proposition, these gi modulo I extensions are in base field Cx, and by calculating normal form of gi with respect to reduced Grosvenor basis of I extension, we can calculate fi's. And then so that we have the scalar differential equation LF that we can write. And for that LF, the Galois group is the given unipotent algebraic group. So these are the steps for the algorithm. And also we can write this matrix differential equation and the relation between this matrix and scalar differential equation, which are in simpler form. So if f is a tuple given, then and so that LF is the monic operator, and then the differential field extension E of f is Picard-Bessou extension for LF if and only if it is Picard-Bessou extension for this matrix differential equation y prime equal to AY, where A is in simple form there. That is there are only non-zero entries in the super diagonals, which are fi's. So if any unipotent algebraic group is given, then we can find a matrix differential equation y prime equal to AY, which is in simplest form, so that its Galois group is that given unipotent algebraic group. And then we'll see as application generalization of Liouville's theorem. So before that, let's recall definition of elementary extension. So a differential field is said to be elementary extension of F if E is generated by elements T1 up to Tn, where each Ti is either algebraic over the field generated by T1 up to Ti minus 1, or it is a logarithm of some Gi, or it is exponential of some Gi for Gi belongs to the field generated by T1 up to Ti minus 1. Then Liouville's theorem says that if an element G is in F, then there is an element Y in an elementary extension of F such that Y prime equal to G if and only if there exist V non-zero elements in F and constant Ci such that G is equal to V prime plus summation of Ci logarithmic derivative of Ui. So in this paper by Chen, he asked for Liouville's theorem for for elementary stable elements, that is elements which are infinitely integrable in elementary extension. So motivated from that question, we define what are n integrable and elementary and integrable element. That is for an element G in F, it is called n integrable in a differential field extension of F if there is an eta such that nth derivative of eta is in G, and if E is elementary extension of F. f, then we say G is elementary and integrable over f. And then we gave this Liouville's theorem for elementary and integrable elements. So if f has an element x such that x prime is 1 and G be an element that is elementary and integrable over f with nth derivative of eta equal to G, then there exist f naught and non-zero elements ui's and polynomials fi's in x of degree less than n such that eta is polynomial linear combination of logarithms of ui up to an element of f, and recurrently we can write G in this form. So even if f has no x such that x prime is 1, then we can also write eta and G, where in this case, in that case, eta will be a constant linear combination of logarithms of ui plus an element of plus a polynomial and up to an element of f. So yeah, that case. In that case, if f has no element x, so that x prime is 1, then also we have a result. And also, Chino asked this nice question that how to classify all the elements in E which are infinity integrable in E, that is unintegrable in E for all n. This problem is still open. And along that direction, this third part in this proposition, that is in that result is in that direction, where in this case, if f is generated by a Lth root of x, then an element G in E is infinity integrable in E if and only if G has this form. And the first two first and second are the examples for if field is generated by e to the power x or logarithm of x, then we have also this expression for G. So now this elementary relations between generalized iterated integrals, this is an ongoing work with my supervisor, and we will see some results on that. So let y be a solution of an algebraic differential equation over f, then one can ask when y1, y2, yn satisfy an elementary relation over f. That is a relation which is a composition of exponential logarithms and algebraic functions in y1, y2, yn over f. So we will not define here the definition, particular like specific definition, but this is the rough definition. And like for example, if y1, y2 satisfy elementary relation, means they will satisfy something like this relation. So for that, prove that if y is an integral of f, that is y prime belongs to f, then y satisfy an elementary relation over f if and only if it is elementary over f, that is in elementary extension of f. And in 1977, then Singer proved that if y1, y2, yn are integrals of f and they satisfy elementary relation over f, then there exist there exist constants, not all zeros, such that this summation ciyi is elementary over f. Now we can so we thought about generalizing this to iterated and generalized iterated integrals. Okay, so before that so Singer also proved this example that if f is the field Cx where x prime is 1 and yi's are elements in an algebraic extension of f such that yi square equal to fiz, cubic polynomial with no repeated roots, then and if for each I this condition is satisfied, then the elliptic integrals, they satisfy no elementary relation over fy1, y2, yn. And then yeah, so then we define what is differential elementary relation, that for generalized iterated integrals. So if eta1 up to eta n are generalized iterated integrals over f, then there exist elements y1 up to yr So because the differential field generated by IISER is a purely transcendental extension, so we will have such y1, y2, yr such that this differential field generated by eta1 up to eta n is the field generated by y1, y2, yr, and we say eta1 up to eta n satisfy a differential elementary relation over F if the elements y1 up to yr satisfy an elementary relation over F. So, and this definition is valid in the sense that it is independent of the choice of the transient base. And we use the term differential because in that relation, eta I and their derivatives will be also be involved. So for that, and also we prove this result. If F contains an element X such that X prime is 1 and eta be an iterated integral of F, and if eta satisfy a differential elementary relation over F, then there exist polynomials Pi each of degree I such that where each Pi is of degree it is less than equal to I actually. Yeah, it is less than equal to I such that this sum is not in F and it is elementary integral of F. And for if F has no x such that x prime is 1, then we have similar result like Liouville's theorem, where in that case this Pi will be constants and a polynomial will be plus a polynomial will be there, which is not in F, is an elementary integral of F. And that can be generalized to generalized iterated integrals, and we can say that if eta be a generalized iterated integral of F, and if eta satisfies a differential elementary relation over F, then there exists an element y not in F such that y is an elementary integral of F. And combining these results, we can prove this corollary that if eta 1 up to eta n be generalized iterated integrals of F, and let K generated by K, which is field generated by yi's, where yi's are integrals, and if it is the largest integral extension of F, then the following statements are equivalent. That is, eta 1 up to eta n satisfy differential elementary relation over F. If and only if there exists constant Ci such that summation Ci yi is not in F, is an elementary integral of F. And this result, so one can say that if some generators of a differential field is given, then one has to look only the integrals. If the linear combination of the integrals satisfy if a linear combination of integral, like no linear combination of integral satisfy no elementary relation, then those generators will not satisfy any elementary relation. Also, this if we assume this eta I to be integrals of F, then this generalizes the result of Singer. That is summation Ci eta I will be in not in F is a elementary integral of F. And from those results, we can also conclude that if F is Cx, x prime is 1, and y be an element such that y square equal to this product of x minus ai, where ai's are all distinct complex numbers, then this elliptic integral and integral of the elliptic integral, they satisfy no elementary relation over Fy. Yeah, and this and the this talk, and these are the references. And thank you all for the attention.
Okay, great. Thank you so much for the very interesting talk.
I finish it. Yeah.
Are there any questions or comments? You can just unmute yourself and ask, or you can also type in the chat if you prefer. So I was wondering about this conjecture of Saoshi Chen. Is there also
Yeah.
Yeah, it is. Yeah, okay. Maybe can you find it?
Yes.
Yeah. So my question is there also a contextual? Somebody is asking for a description of those infinity integrable elements. But is there already a contextual description, or is not even clear
No. Yeah.
what the description
Yeah.
could be?
Yeah. He has also given a description for the conjecture. But recently I met him, and he was saying that he had some counter example for that conjecture. So I don't know, but maybe there is some conjecture. So I did not put the conjecture specifically here, but the question is still there.
Okay.
Like how to classify the elements which are infinity integrable. Yeah. This.
Okay. Here it is.
Hmm.
Okay. Are there any other questions? Okay, if not, so let's okay, thanks again for the very nice talk. And so I believe, if I remember correctly, we don't have talks in the next 2 weeks, but there's still gonna be, I think, 3 more talks before the end of this year. All right, so I'll see you all. Looking forward to seeing you all again in 3 weeks.